Hi everybody and welcome. In this video you're going to learn about Kapre, one of my favorite audio processing libraries. What's specific to Kapre is that it allows you to run audio transformations, like for example a short-time Fourier transform or applying filter banks directly on your GPU and within your Keras models. In other words, you can think of Kapre as the audio processing unit for Keras. It's the equivalent of Torch Audio for PyTorch. Kapre was developed by Keunwoo Choi, already research scientist at Spotify and ByteDance. The library is really interesting and I really love its philosophy. Basically, all the different audio transformations like short-time Fourier transform or transforming magnitudes to decibels are Keras layers that you can add within your model. This brings certain advantages, but also certain disadvantages. Let's take a look at the advantages first. Now, first thing is that if you can add all the different audio transformations as layers within the model, this means that all the different DSP parameters, like for example hop size or frame size, are going to be optimizable. You can use your optimization algorithm to find the best value for these parameters. This is very handy and it's going to save you a lot of time. The second big advantage is that your system is going to be quite easy to deploy and to use for inference. Why is that the case? Well, because you run audio pre-processing directly within the model, which basically means that you don't have a pre-processing unit that's external to the model and that's a dependency to the model. Usually when you use pre-computation, what happens is that you have to pre-compute certain transformations on the audio, and once you have the results you can feed them into the model, but the model, it's an external entity. But with Kapre, the audio pre-processing step is already embedded within the model. So you don't have a separation between the pre-processing step and the inference side. Everything can be done in the same space, the space of the model, just because the audio pre-processing happens to be a simple layer, Keras layer that you can easily add. So this makes your deployment very easy, and at the same time it makes your inference super easy because all you need to do is pass in the waveforms and everything will be taken care of for you by a single model. There are also some disadvantages in using Kapre. Every time you run training, all of your waveforms need to be transformed time and again. So the transformations, the results of the transforms are not cached and then reused. So this is going to take more computation and more time. This is Kapre's documentation in Read the Docs. In this left side menu under API, you can see the different modules available which group functions and layers that are semantically similar. Let's take a look at them one by one. We'll start from time frequency. So within this module, we have all Keras layers that deal with time frequency representation. If you're not familiar with the concept of time frequency representation, don't despair, because I have a whole series on audio signal processing for machine learning that you can check out. I'll leave you the link up here. And there I extensively talk about time frequency representation of audio as well as other types of representation. Okay, let's take a look at the different audio transformations that we have here. The first of which is the SDFT, which stands for short time Fourier transform, which is a fundamental representation in audio processing for deep learning. Now, we should always remember that these objects, these classes, will create Keras layers in the end that you can easily add to Keras, to your Keras model. Okay, another transformation that we have in this module is called inverse STFT, so the inverse of the short time Fourier transform. We have the magnitude that allows us to extract the magnitude from a complex input, like a short time Fourier transform. We also have another transformation that extracts the phase from a complex input. We have this one called magnitude to decibel. So we pass from magnitude to decibel, applying a logarithmic transformation. And we also have this one, which is very handy, apply filter banks, which you can use to apply different filter banks, like for example, MEL filter banks if you want MEL spectrograms. Right, there are a few other transformations, but I'm going to skip them. You can check them out later on. So here we have the second module, which is called a signal. So here we have all the Keras layers and transformations which live within the sort of like time representation of audio, so directly on the signal. Okay, so let's take a look at a few of them. For example, here you have energy. So with this, you can extract the energy content directly from a waveform. And then if you move down, for example, down here, so if you have log MEL spectrograms, then you can move to MFCCs, so MEL frequency cepstral coefficient. This is also another representation, another feature that's extensively used within audio processing for machine learning. It's a more traditional one, right? Really. Right now, we tend to use more spectrograms, but MFCCs are still very used. Okay, now let's move on to another module that's called composed. This one is really interesting because it provides you with high-level functions that give you high-level layers that are made up of a bunch of other Kapre layers. Let me explain what I mean by taking a look at this first function here. So it's called get STFT magnitude layer. So here we get a high-level layer that chains under the hood 2 or 3 Kapre layers. The first of which is a short-time Fourier transform. So we extract that, then we extract the magnitude out of this, the complex result of the short-time Fourier transform. And then, if we want, we can also apply a transformation that moves the magnitude to decibels. Okay, as you can see, these high-level functions chain together lower-level Kapre layers, which is very, very handy. Another one that we have here, it's called get MEL spectrogram layer. So here, this higher-level Kapre layer has multiple Kapre layers. So the first of which is the short-time Fourier transform. Then again, we extract the magnitude. But at this point, we want to apply a filter bank, specifically the MEL filter bank, so that we can get a MEL spectrogram. And finally, we can apply a magnitude to decibel transformation once again. There are a few other functions here, but I invite you to discover them at a later point. Okay, so now we'll skip to the time frequency TF light module. This is something very, very interesting because it provides a bunch of audio transformations that are compatible with TF light. Now, what's TF light? If you're not familiar with that, I really encourage you to check it out. TF light, it stands for TensorFlow Lite, and it's a lightweight version of TensorFlow, which runs deep learning models on edge devices like the Raspberry Pi or Arduino. So here you can see there are a few audio transformations that are sort of tricked to work on TF light. And here you have the short-time Fourier transform, and down here you can also extract the magnitude as well as the phase. And all of this is going to work directly on TensorFlow Lite, which is very, very nice because there are many applications in audio processing and music processing that need to happen on edge devices like Arduino or Raspberry Pi, where computation is quite limited. So this module is very, very handy. Now that we have a sort of overview of the different features available in Kapre, let's use them and let's see them in code. Okay, you guys, we are ready to start coding a Kapre example. What I want to build here is a model, Keras model, that has an audio backend that allows us to pre-process audio waveforms and extract MEL spectrograms. We're going to implement this in 2 ways. One is going to be a little bit more convoluted because we're going to build all the different Keras, Kapre layers, and the other one we're going to use the very handy get melt spectrogram layer utility function that comes from the composed, I believe, model in Kapre. Okay, but the first thing that we should do before anything else is to install Kapre, and that can be easily done via the terminal, typing pip install Kapre. Okay, so I haven't installed anything here because I already installed it, but it should work for you. Now, on the documentation, it says that Kapre works well with Python 3.6 and 3.7. I'm using Python 3.8 for this example, and Kapre is working like a charm. I would say like a pie charm. Okay, so now let's get started. First thing we want to do is to import a bunch of things that will help us. So first of all, we'll import from Keras, we'll import sequential, the sequential model. Then we'll import a bunch of Kapre layers. So we'll do from Kapre.time frequency. Here we'll import all the layers that are necessary for creating a melt spectrogram in the end. So SDFT, then the magnitude, then apply filter bank, and finally we'll use this transformation magnitude to decibel. Now, there's a cool thing here. You don't really need to go to time frequency, to the time frequency model to import all of this, because they can be imported directly from Kapre, which is very handy. Okay, I'm also going to import from Kapre.composed get melt spectrogram layer, which is the sort of very handy function. Okay, next we are going to set a few constants that we're going to need to specify parameters for our audio processing. First of all, we should establish the clip duration. So this we're going to pass waveforms, right? Audio files in, like wave files. And now we want to know what's the duration of these audio files. And the duration is going to be equal, let's say, to 5 seconds. Now, another important constant here is the sampling rate. And we can set the sampling rate equal to 1000 Hertz, for example. Then we need to specify the number of channels that we'll have in our audio files, and let's say 2. This means that we're dealing with stereo audio files, but if we had 1, we would have been dealing with mono files, but let's say 2. Next, we want to establish the input shape. Okay, and this is going to be equal to a tuple with 2 items, the first of which is going to be equal to the clip duration multiplied by the sampling rate, okay? And the second one is going to be equal to the number of channels. So in this case, we are using the so-called channel last mode. And yeah, let's just keep in mind this point, because it's going to be useful when we define our layers. Okay, so next we need to implement the main function here, and we'll call it create a model with audio unit. Okay, perfect. So first thing that I want to do is create all Kapre layers, and then I'm gonna add Kapre layers to a sequential model. Model, and yeah, let's stop here for now. Okay, so first thing, we want an STFT layer. Okay, so for this we should pass quite a lot of parameters in. Okay, so here you can see that there are indeed many parameters that we can pass. So first of all, we'll pass the FFT. So this is the number of FFT points that we want in our short-time Fourier transform, and we'll set this equal to 1024. Then we're going to pass the hop length. Oops. there's a comma there, and the hop length is going to be equal to the, I'd say like half of the frame size, right? And then we're going to pass the input data format, and we say here we should say whether like we are channel first or channel last, and here we'll say channels last, and we should do the same thing up here, down here, for the output data format. Okay, and I think there's still a thing missing. NFFT, hop length, and input data, output data format. No, I think that's it. I mean, of course, like there are other parameters like the win length, the window name. So if we want to use, for example, a Han type of windowing, and then pad begin, pad end, but this is like too much detail. We don't want to get into that level of detail. Okay. So now we have the SDFT layer. Next thing, we want to create a magnitude layer. Now, magnitude layer. And for this, we just need to, start or instantiate magnitude, and that's it. We want to implement the apply filter bank layer. And we instantiate and apply filter bank object, and here we should pass a couple of things, well, a few things. First of all, the type, and the type is going to be equal to mel, because we want to apply a mel filter bank to get mel spectrograms, and then we should pass the so-called filter bank quirks. Okay, so filter bank quirks, so these parameters are numerous, and so we should check them out here. So we can, copy this. That comes directly from an example. Okay, and first of all, the sample rate we already have, and it's this one. So the sampling rate. So the number of frequencies is equal to NFFT divided by 2 plus 1. In this case, we already have this. So it's the NFFT divided by 2, 512. Plus 1, so 513, so that's what we should expect. Then the number of melts, let's say we want, just 64 melts, and then the Fmin and Fmax, these are the minimum frequency and maximum frequency sort of like accounted for by the filter banks. And so, let's leave like 0 as the minimum frequency and 8000 Hertz as the maximum. Okay, so now we have all of the parameters which we can pass in here, and we'll get back a Kapre layer called apply filter bank. Finally, we have to implement the magnitude to decibel layer. Okay, and for that, we just instantiate this object, and that's it. Okay, so now we have all of these different layers. The next thing to do is to create a sequential model. So we'll do model sequential. This is a Keras sequential model. And now we are going to add all of the different layers here that we created. So we're going to add the STFT layer, then the magnitude layer, then the apply filter bank layer, and finally the magnitude to decibel layer. Great. So now we have all of our audio backend, and we can do a model.summary to see a summary of the model that we've built so far. Okay, so now let's create a script real quick. So we'll do a if name is equal to main, then we're gonna create model with audio unit. Let's run this and see what happens. Okay, it's running. We have an error, hop length. I think there's a typo here. Okay, let's just fix that. So the T should come before the H, hop length. Let's rerun this and see what happens. And we have another error. So this model has not yet been built by calling build batch of data. Oh, I know what's happening here. Right. I forgot to pass the input shape here. So we should pass this input shape to STFT so that we know the input shape, and so the model is not going to comply because it will know the input shape. Let's rerun this and see if we're lucky. And there we go, third time lucky. So we have our sequential model with all of the different layers, the first of which is STFT. This is the output shape, and that's what we expect. This 2 is the number of channels. Then we have the magnitude layer, apply filter bank. So here we apply the MEL filter bank. And then we have the magnitude to decibel transformation. Okay, so I'm gonna save this shape here because we're gonna need it. So I'm gonna comment, this one out, but add it here nonetheless. Okay, so now what I want to do is add a simple VGG model, VGG16 model in front of this audio backend. In other words, we want to add VGG16 to the model that we've built so far. Okay, so let's create VGG16. Okay, so for that, we need to import TensorFlow, STF, okay, and here we'll do a tf.keras.applications.vgg16. First, we have to pass the input shape, and the input shape is equal to this tuple here. And why is it equal to this? Because this tuple is the shape of the tensor that is the final tensor that is output by the audio processing unit. So that we use as the input for the remaining part of the model, which is VGG16. Okay, then we should say that we want for the weights to be completely randomized so that we don't use some pre-trained VGG weights. And we should also say that we want, say, 2 classes. So this is the number of outputs, the number of labels that we expect, and that's equal to 2. Okay, so now the next thing to do is to add VGG16 to the model, and now that the model is complete, we can just call model.summary, and we're going to have our nice summary of the complete model. Let's take a look. Yeah, there we go. So the first 4 layers make up the audio backend, and then we have this VGG16 functional model whose output is equal to 2, and these are the 2 labels that we expect. Perfect. So this is completely correct. So as you can see, it's very easy to build an audio backend that does pre-processing, audio pre-processing in real time, leveraging your GPU directly within Keras and using Kapre. Okay, next thing that I want to do, guys, is basically rebuild the very same model, but this time using the utility function get MEL spectrogram layer. And as you'll see, this is really, really fast. So we'll do a define create model with audio unit from utility function. It's a very long name, but yeah, you get the idea. Just let's differentiate that from this. Okay, so what should we do here? Well, this is actually quite straightforward, because here we're going to have a MEL spectrogram layer, and that is going to be equal to get MEL spectrogram layer. Here we have to pass a lot of parameters. Now, if you want to check all the different parameters, you can just jump into the function. I can do that easily here in PyCharm with a shortcut Ctrl+B. I jump in here and I see all the different parameters here in the definition of the get MEL spectrogram layer function. Okay, so Let's get back here. We can certainly take all of these things. And I think all of them should be okay, yeah. So the number of FFT points, hop length, the input data format and output data format, and the input shape. I can take all of these things and put them down here as a reference and then pass them in. So we can pass the sampling rate, then the number of mels, and that's equal to 64. And then for fmin and fmax, I think, yeah, the name is mel fmin, that's equal to 0. And finally mel fmax, that's equal to 8000. Okay. Yeah, this looks good. So now we have our mel spectrogram layer, and we can once again create a sequential model. So we'll do a model sequential, and then we'll do a model.add, and we'll pass in the mel spectrogram layer. To finish this one off, we can just copy the VGG over there and paste it here. So we create our VGG16, we add it to the model, and finally we print a summary of that. Okay, so let's try to run this and see if we can get the same results. And there you go. Yes, we have the very same result as you can see here. We have the first layer, which is the sort of like higher level layer sequential model that embeds all the different steps that we created previously. And then we have the VGG16. And that was it for Kapre. I hope you now have a good understanding of how you can use the library and different use cases that this library can help you with. Of course, there are way more features that you can discover, and I highly encourage you to explore the library by yourself and to play around with it. But now you should have the basics. If you want to learn more about audio and music processing, you should definitely subscribe to the Sound of AI channel, this channel, and join the Sound of AI Slack community if you haven't done so. There you have more than 5,000 people who are super passionate about all things ML, AI, music and audio. So it's a very nice community to be in, and it's very, very supportive. You'll find the sign up link to the community in the description box below. That's all for today. I hope you had a lot of fun. I'll see you next time. Cheers for now.